In today's class, first and foremost, I'm gonna teach you a general purpose approach to solve any linear differential equation with constant coefficients. That is the approach that you should remember. If you happen to come across a nonlinear differential equation, nonlinear means one burger for $1, two burgers for $2, five burger for $3. If you get that type of an equation, then typically we do not solve those equations by hand because there are very few differential equations that you can find an analytic expression in terms of sine, cosine, tan, some crazy functions. So you are going to use some numerical equation solver like MATLAB. Most of the robot equations are nonlinear. We typically do not solve them by hand. As a matter of fact, we don't even form the equations. But it's extremely important for you to understand what is a differential equation and what is the general purpose technique to solve differential equations that are solvable. So everyone, please pay attention. I know you spent an entire course on differential equations, but I'm gonna give you just one single approach that would work for differential equations. Now, understand differential equation is an equation that involves derivative. Okay, differential equation that involves derivative. Now, the class of differential equations are x dot is equal to ax, wherein x dot means x dot is equal to dx by dt. And in last class, I tried to solve this differential equation and came up with answer. You can also have an equation which is of the form x double dot plus maybe some x dot plus maybe some x. This is also a differential equation because x double dot means two derivatives, which is d by dt of dx by dt, which is also written as d2x by dt square. Now here x of t is the independent variable. X is the dependent variable and time t is an independent variable. Now, before I go into talking about differential equations, I want to ask you a very simple question. What is a solution of an equation? So, say for an example, if you have an algebraic equation, algebraic equation means 5x is equal to 5. It is an algebraic equation. So, what is the solution of an equation, whether it is algebraic or it is differential? Okay, at the end of the day, the solution of an algebraic equation or a differential equation is a constant or a function. If we substitute that constant or a function on the left-hand side, we should get the right-hand side, or the left-hand side is equal to right-hand side. How you find that constant, how do you find that function is totally up to you. You could be a psychic and say, oh wow, look at this equation and this is the function. If the left-hand side is equal to right-hand side, that is the solution of an equation. In the case of an algebraic equation, we typically substitute constants. What it means is I can say 5x. X is equal to 0. On the left-hand side, I get 0. on the right hand side I get 5, that is not the solution. If I substitute x is equal to 1, my left hand side equals my right hand side, so that is the solution. Everyone understood this? So solution of an equation means once you substitute that constant or a function, your left hand side should equal to the right hand side. How you find that equation or how you find that constant, how do you find that function is totally up to you. Now let's look at the differential equation that we have on the right hand side. The differential equation, you are trying to look for a function, and that function should be dependent on time, so that when you substitute that function on the left hand side, when you substitute that function onto the right hand side, left hand side is equal to right hand side. Everyone understood this? So differential equation solution means we are trying to identify a function that will satisfy that equation. I want to start with a very simple case. Look at that equation that I have, x dot is equal to ax. What can I substitute as x that would satisfy x dot is equal to ax? Very simple. 0. Right? If my x is 0, my x dot is going to be the derivative of 0, which is 0. Left hand side 0, right hand side 0. So x is equal to 0 is a solution of the differential equation shown over there. X dot is equal to ax. Solution of the differential equation x double dot is equal to x dot plus x. X is equal to 0 is a valid solution. Everyone understood this? But it is called as the trivial solution. Trivial means non-important, right? So like rate cars, robotics 1 course is trivial. It's not important. So it's a trivial equation, which means by looking at that function, you can say x is equal to 0 is trivial solution. And there is a lot more thing that goes behind whether the trivial solution is stable or unstable, or there are a lot of stability issues that come in the picture. But I'm not interested in the trivial solution. I'm interested in a solution that is actually meaningful. Now, what I want to do is, I want to start with a very simple case. In the last class, and the stuff that I'm going to discuss is extremely important, because this is the crux of differential equation. Now, we looked at a spring mass system. Do you agree with me? We have mass, we have spring, and then we applied Newton's law, we applied the energy technique, and we found out the equation mx double dot plus kx is equal to 0. Do you agree with me? This is the equation that we derived in last class. This equation, since there are 2 dots on the x, this is second order. Ordinary. Why ordinary? Because the independent variable is only 1. It's not 2. So ordinary. Unforced, which means right hand side is 0, which is also called as non-autonomous differential equation. Please note, m is a constant. M is a constant. K is a constant, which means the mass is not changing. The stiffness is not changing. Whenever you have an equation of this type, and I can tell you in your undergraduate differential equation class, you have seen the variations of exact same equation in multiple forms. And you can add, it can be m triple dot, or it could be m 4 dot, whatever equation that could be. the most general way to solve this equation is I'm going to assume, okay, I'm going to assume a function for x. I'm going to assume a function for x. I'm going to substitute that function on the left hand side of that equation. And if all said and done, if I get the right hand side is equal to 0, which means the function that I have found out is the solution of this differential equation. Everyone understood this? Here is what I'm going to do. I'm going to assume a function. I'm going to substitute the second derivative of function in x double dot, function as x, and see if I get left hand side is equal to right hand side. And if my left hand side is equal to the right hand side, do you agree with me? That is the solution of differential equation. Everyone understood this? Whenever you see a differential equation which is linear, constant coefficient, there is no forcing on top of it. The only thing that you should substitute as x is x is equal to maybe a constant, x of t is equal to maybe a e to the lambda t. This is the only thing that you should substitute as x. Now, what are we missing? I do not know what is the value of a. I do not know what is the value of lambda, but I know what is e. And t is my independent variable. Everyone understood this? If you refer to the notes before the break, I derived this equation by solving x dot is equal to ax. Now, so here is the key. This is the only thing, and I really mean this, this is the only thing that you should remember from your differential equation class. Now, what I'm going to do is I'm going to substitute. So, x dot of t, do you agree with me? A is a constant. E to the lambda t is lambda a e to the lambda t. Do you agree with me? X double dot of t is equal to, now I'm going to get lambda square a e to the lambda t. Do you agree with me? Now I'm going to substitute m x double dot as lambda square a e to the lambda t plus k a e to the lambda t is equal to 0. Do you agree with me? Now understand, I have 0 on one side. So a gets cancelled. A gets cancelled. I divide left hand side and right hand side by a. I divide left hand side and right hand side by e to the lambda t. So this gets cancelled. This gets cancelled. So what am I left with? I'm left with m lambda square plus k is equal to 0. Do you agree with me? Here, please note, m is known, which means m could be 1, 2, 3, 4, 5. K would be known, which would be 1, 2, 3, 4, 5, because m is the mass. It's a physical property. It has to be positive. K is the stiffness. It's a physical property. It has to be positive. Now, what I have here is m lambda square plus k is equal to 0. And only unknown here is nothing but lambda square. Everyone understood this? So what I can do is, I can find out the value of lambda square. Lambda square is equal to minus k by m. Do you agree with me? So lambda is equal to plus minus I square root of k by m. Are you with me? Now we have found out the solution of differential equation. Now understand, there are two values of lambda. If there are two values of lambda, my equation x of t would look like a1 e to the plus I square root of k by m times t plus a2 e to the minus I square root of k by m t, which means this is the solution of the differential equation. If I plug this solution in, mx double dot plus kx is equal to 0, my left hand side would be equal to my right hand side. Everyone understood this? Now, this is where the things become a little bit interesting. Now, we have this complex quantity here. Do you agree with me? This is a complex quantity. This is also a complex quantity. Now, if you look at the physical solution of the spring mass system, we saw in last class that solution is going to be something like oscillatory solution. Do you agree with me? Now, it has to be some type of a sine and cosine combination. Now, this equation, it looks different because it has square root of k over m. But let me tell you that the equation that you see here can be represented into cosine and sine form using Euler's identity. Which means what you can do is this equation can be written as a1. I can write down, so in case if you are wondering, so e to the I omega t is equal to, does anyone remember? Cosine omega t I sine omega t. Now what that means is I can write this expression, and it's extremely important, as cosine square root of k by mt plus I sine of square root of k by mt plus a2. Now you got the minus sign, so basically this becomes cosine square root of k by mt minus I sine square root of k by mt. Now please understand, I have cosine k omega t here, cosine k omega t here, so that can be combined. So I can write this down as a1 plus a2 cosine square root of k by mt, and here I have I sine and I sine. So what I can do is I can plus say a1 I minus a2 I sine square root of k by mt. Are you with me? Now, please understand, a1 is a constant. Constant plus constant is a constant. I is a constant. A1 is a constant. A2 is a constant. So I can rewrite this as something like C1 cosine square root of k by mt plus C2 sine square root of k by mt. And this is the solution of the differential equation. What does this solution of differential equation means? It means if you look at the way that mass is going to oscillate, that mass is going to oscillate in some type of simple harmonic motion. This simple harmonic motion would have some cosine component, it would have some sine component, and C1 and C2 are nothing but the initial conditions for that sine and cosine component, which means C1 and C2, they are nothing but the initial condition for the differential equation. To solve the differential equation, you have two derivatives, which means you have to integrate it twice. If you integrate it twice, so you will have to add two constants of integration. Everyone understood this? Now, a slight twist. If we have a system, something like this. So now you have a mass, you have a spring, and you have a damper. The differential equation for this system is given as mx double dot plus cx dot plus kx is equal to 0. You would use the exact same approach. So you would assume x is equal to e to the lambda t multiplied by a constant a, x dot is equal to a lambda e to the lambda t, x double dot is equal to a lambda square e to the lambda t. Substitute everything in this expression. So you are going to get m a lambda square e to the lambda t plus c a lambda e to the lambda t and plus k a e to the lambda t is equal to 0. Once again, a will get cancelled. A gets cancelled. E to the lambda t would get cancelled. And finally, now you have an expression m lambda square plus c lambda plus k is equal to 0. Do you agree with me? And now we have to solve this equation. So this equation is a quadratic equation which can be solved using the technique minus b plus minus square root of b square minus 4ac divided by 2a. Do you agree with me? So you would get lambda 1 and you would get lambda 2. Lambda 1 would have, you would find lambda 1 by substituting minus c plus sine. You would find lambda 2 by substituting minus c minus this term. Everyone understood this? Lambda is called as the eigenvalue. So lambda is called as the eigenvalue. Now, why it is called as eigenvalue? Because it dictates the behavior of that system. Question? Yes. So, okay. Clearly, Laplace, since you asked, what is Laplace transform? Good. Classic textbook answer. Anyone else?
Decomposes a function into sine and cosine.
That's Fourier transform. Anyone else?
Translation.
Yeah, I'm sure some mathematician taught him Laplace transform, right? Okay. Why is Laplace transform important? Everyone knows logarithms. Okay. Logarithms we studied in high school. Why did we use logarithms? Here is the basic idea. what you have is in 1950s and 60s, they did not have calculator. They did not have chat GPT, but still they have to send man onto the moon. So they had to multiply these huge numbers, this huge number multiplied by this huge number will take huge amount of time. Everyone understood this? You have this huge number, multiply this huge number because astronomical distances. You are going to get a huge number, but to calculate that, you will take a lot of time. Everyone understood this? So here is what logarithms do. Once you take log of this huge function, you get a small number. You agree with me? You get log of this huge number, you get a small number. You agree with me? And this multiplication gets converted into addition. So you can add this small number plus this add small number, get a small number, find the inverse logarithm, and you have your solution. Everyone understood this? So what did we do? Multiplication operation, we converted to addition operation by performing a log transform. Everyone understood this? We did that to make our life easy. Laplace transform does the exact same thing. Now what you have is you have a differential equation, which is x double dot plus kx is equal to 0. If you want to solve that differential equation, you will have to go through the analysis that we have done. You will have to perform integration minimum 2 times if it's a second order differential equation. But once you take Laplace transform, that differential equation gets converted into an algebraic equation. Just like your logarithmic log transform, if you take a Laplace transform, the differential equation, which is difficult to solve or takes more time, gets converted into an algebraic equation. And once you get the equation in algebraic form, with just plus or minus, you find the solution in the Laplace domain, take the inverse Laplace transform, and now you have the solution of the differential equation. Exact same process. Everyone understood? Yeah.
I'm not understanding, like after getting the value for lambda, why are we modifying our assumed function? Because our assumed function was just a map to the power lambda, but then after getting lambda one, lambda two, just added 4. How is it same?
Okay. The answer to that is when we solved this, and actually this is an important question. You agree with me, lambda can have potentially 2 values. Okay. Which means if I substitute lambda is equal to plus square root of k by mi, that equation will be satisfied. You agree with me? If I substitute lambda is equal to minus I square root of k by m, that equation will be satisfied. You agree with me? Or if I write down an expression which is the linear combination, addition or subtraction of lambda plus I square root of k by m and lambda minus I square root of k by m, will be satisfied. And that's why I'm using those two functions. It is as simple as if you have a simple harmonic motion, if you assume that motion to be sine, the equation will be satisfied. If you assume that to be cosine, function will be satisfied. So what we want to do is we want to add these two possibilities together, and then that is going to be my final and actual solution. We are solving a linear system. So which means if A is the solution, if B is the solution, A plus B is also a solution. Does it make sense? So that is the idea here. Now, the last thing which I want to tell you here is, now C square minus 4km is a critical parameter. Now, please understand what happens. If square root, so let's say if C square minus 4mk is equal to 0, or c square minus 4 mk could be greater than 0, or c square minus 4 mk less than 0. These are the three cases where the system could be underdamped, system could be critically damped, or system could be overdamped. For an example, if c square minus 4 mk is less than 0, please understand that here you are going to get complex conjugate roots. So system is going to be underdamped. Now, if you have c square minus 4 mk is equal to 0, then you do not have any right hand side, so the system will be critically damped. And then if you have this, the system will be over. So again, these are the eigenvalues, and depending, C is the damping coefficient. So now I want to give you a very simple example of what do I mean by system is underdamped, overdamped, or critically damped. And simple example is you have that door which is attached to a spring mass damper that makes that door close. So we have one door here, one door, two doors there. So you open the door and door closes on its own. Now please understand, depending upon the damping, spring parameters and the mass parameters, there are three ways a door can close, and you have seen this. So one way the door can close is you open the door, you let it go, and door kind of wants to go like this. It means it actually hits the frame. The door wants to go like this. This is the behavior of an underdamped system. So system kind of oscillates and then damps down. The second case is you open the door and then the door actually closes very smoothly without hitting the frame. So it actually closes. This is the critically damped case. And in the case of overdamped case, you open the door and then door takes very long time to get back to its initial position. That is the case of an overdamped system. Everyone understood this? You probably have seen this. Imagine that you are driving a car and the suspension is fairly new and you hit a pothole or you go over the bump. So basically those potholes input is dampened. So actually the body comes to rest very quickly. Sometimes if you have worn out springs, then you go over the pothole or you go over a speed breaker or anything, a rock, then you will see you start oscillating like this, which is like you have worn out spring. That is an underdamped behavior. And then if you have a critically damped system, you basically go over the pothole and then the car takes long time to come back to its original position. So that is dictated by the amount of damping, mass, and the spring stiffness. So critically damped systems are typically desired because basically they go to the equilibrium position very smoothly. They don't cross the equilibrium positions. Everyone understood this? Okay, now the important part. In last class, I talked about the energy techniques. Now, energy techniques are the fundamental techniques to solve physical equations. So, energy approach is applicable to celestial dynamics. It is also applicable to quantum mechanics. In the last class, I gave you a very simple approach wherein I said, if this system has two types of energies, kinetic energy and potential energy, we will find out the total energy, we'll take the derivative of total energy, if the derivative of total energy is equal to 0, which means energy is not changing, energy is neither increasing nor decreasing, the system is simply stable. If the rate of change of energy is decreasing, which means energy is going down, 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 then the system is going to become stable at some point of time. Or if the energy rate is increasing, that means the system is becoming unstable. So that is what we discussed in last class. Today, I'm going to introduce you to a very, very powerful technique, which is called as Lagrangian approach. And why this Lagrangian approach is important? Because it can be applied to any type of multi-body system. As long as you have a multi-body dynamic system, this Lagrangian approach can be used. There are two classic energy techniques. In the last class, we talked about this T is equal to kinetic energy plus potential energy. So total energy is kinetic energy plus potential energy. Kinetic energy is given as P, potential energy. So if I were to say T and V. So kinetic energy is typically denoted by T. So I need to write this down as total energy. Total. This approach is called as Hamiltonian approach. In Hamiltonian approach, you are going to look at the total energy. Now there is another approach which is called as the Lagrangian approach. There, what we do is we find T minus V. This is called as the Lagrangian approach. Now, what happens in Lagrangian approach? You look at the system, find out the potential energy of the system. You will find out the total potential energy. You look at the kinetic energy of the system and you'll find out the total kinetic energy. And then you will find out this Lagrangian. And what you do is you will find out the equations of motion by using this simple equation, d by dt partial L by partial x dot minus partial L by partial x is equal to 0. Now, what is this? So please note, this is the partial derivative with respect to velocities. With respect to velocities. This is partial derivative with respect to positions. And this is the ordinary derivative with respect to time. Now, this may look complex, but I'm going to solve one or two problems by hand. And then we would use MATLAB from start to end. So what we would do is, we are going to use a MATLAB code. And MATLAB would form this Lagrangian. MATLAB would form these differential equations. And MATLAB would solve the differential equation. This approach works for linear as well as nonlinear systems. So first, let me show you how this approach works by taking an example. The example is the same example. I have the spring mass system. I have the spring mass system. I have M, I have K. First, I need to find out the kinetic energy. Kinetic energy is T. Do you agree with me? It is going to be 1/2 m x dot square. Potential energy is V, which is 1/2 k times x square. Do you agree with me? Then I would form the Lagrangian. Lagrangian is T minus V. So T minus V is 1/2 m x dot square minus 1/2 k x square. You agree with me? For this problem, I'm gonna find out these terms separately. So partial L by partial x dot, which means x is equal to 0. So all the terms, so here, when I do partial L with respect to partial x dot, sorry, x is equal to constant. X is equal to constant. Which means the first term is gonna be m x dot plus 0. Do you agree with me? Everyone understand what a partial derivative is, right? Partial derivative means I'm gonna just take the derivative with respect to x dot. If there are any other terms in x triple dot, terms in x to the x4 dot, all those terms are treated as constant. So here, when I take the derivative, I would be taking the derivative of only this first term. So 1/2 m x dot square is 2 times 1/2 m x dot. And it's a partial derivative. And here, since x is a constant, when I take the derivative of this, the derivative is going to be 0. Everyone understood this? Okay. The next thing is I'm going to take partial L by partial x. And same story. The first here, x dot is equal to constant, which means I have this term as 0. The first term will be 0. And the second term is going to be minus 1/2 times 2 times kx. So this term is going to be minus k times x. Do you agree with me? Now look at the Lagrangian equation. Lagrangian equation is d by dt partial L by partial x dot, which is m x dot, minus partial L by partial x, which is minus k times x, and is equal to 0. So I have this expression as mx double dot plus kx is equal to 0. Do you agree with me? This is the same equation that we got when we try to solve using Newton's approach or Hamiltonian approach. Everyone understood this? No matter how many degrees of freedom I have, I could have 1, 2, 3, 4, 5, 6, 7, 8 hundreds degrees of freedom. Lagrangian approach will always work. What is the issue with the Newtonian approach? Newtonian approach is not bad. Newtonian approach works very well if you can draw the free body diagrams and apply summation of force is equal to mass times acceleration at every free body diagram. Have you looked at, if you look at this, I have not drawn free body diagram. I have not even drawn the coordinate system. I don't care because my potential energy is a positive scalar function. My kinetic energy is a positive scalar function. I just found out the kinetic energy and potential energy for this mass, and boom, I get this differential equation which is given over there. Everyone understood this? So now what I'm going to do is I'm going to take you to MATLAB and I'm going to show you a MATLAB script that actually I have uploaded on Canvas, but I will make it visible. How do we solve super complicated robot dynamical system using Lagrangian approach? Yeah. Okay. Hamiltonian approach is typically used for continuous systems. Now, what it means is if you have a soft robot, or if you have a robot which is sort of a beam robot, then the Lagrangian approach will not work. Lagrangian approach works very well for something called as the discrete system, which means you have mass, you have mass, you have mass. Hamiltonian approach works very well when you have a distributed mass system. So Hamiltonian approach typically is used if you are trying to solve soft robotics problem, or if you are trying to solve, I don't know if you have seen those chemical robots, or if you are trying to solve the robots that are in the form of a beam. Lagrangian approach works very well when you can discretize. So basically you have this beam and you discretize this as spring mass, spring mass, spring mass, spring mass, spring mass. In that case, the Lagrangian approach gives better result. And typically the robots that we are going to study in robotics 1 are discrete systems. But I'm pretty sure if you take soft robotics course, soft robots, you can use discrete approximation using flexible bodies, but you will have to look at the continuous system and continuum, basically constitutive relationships to solve the robot problems. Okay, any other question? Now what I'm gonna do is, I'm gonna take you to MATLAB and I'm gonna explain to you how this Lagrangian approach works. Yeah. Yes, you can apply the, as a matter of fact, I will show you the system to the demo. Any other question? Okay. Now, this code is not visible yet, but what I want you to do is I want you to follow the whole MATLAB thing with me. That way, okay. So the most important function here is called as this Euler-Lagrange function. And this is a very complicated function and it is written by MathWorks. So I did not write this function, but we are going to use this function to solve robot problem. And you can do a lot of interesting things with this. Now, the Euler-Lagrange problem, this function derives the system differential equation based on the system Lagrangian. Which means if I give you a super complicated robot, your idea, the basic idea there is find out the total kinetic energy, find out the total potential energy for that robot. And then substitute the expression for kinetic energy, substitute the expression for potential energy, and then this function will do the rest. Now, if you go through this help, it gives you a very good help, but this function is quite powerful. It will not only create the MATLAB function, but it will also create the Simulink block that you can actually use. And this is actually super important because if you use this as a Simulink block, then you can feed this to your actual robot visualization and you will see the robot will behave the way you want it to behave. Now, here are some examples and I would encourage you to try these examples So the first example is the projectile motion. You are throwing a rock with some horizontal velocity, some vertical velocity, or you are throwing the rock at some velocity and at an angle. It is an inverted pendulum. Then there is another example, which is a simple pendulum. There is example of double pendulum. There is example of RLC circuit, and so on and so forth. But this function is, I wouldn't touch any of this function. So you are not going to touch this function. You will use this function the way it is given. What you would do is, you would open this function, equation, run this first. This is going to be your driver function for all your problems. So if I give you a single degree of freedom robot, if I give you a multi-degree of freedom robot, if I give you a 100-degree of freedom robot, you would make changes to this. And there is very systematic way to approach this. So everyone, please pay attention. So I'm trying to solve the spring mass problem using Euler-Lagrangian approach, but I want to kill all the birds in one shot. So what I want to do is, I want to derive the differential equation of motion. I want to solve the differential equation of motion, and I want to plot the solution of the differential equation of motion. Everyone understood this? So earlier, with Euler-Lagrange, we just derived the differential equation of motion. We did not solve it. We did not plot it. But this script will actually find the differential equation of motion, find the solution of differential equation of motion, and at the end, plot the solution of the differential equation of motion. Everyone understood this? And it is not just restricted to linear. You can use even non-linear systems as well. So first and foremost, we are trying to solve spring mass system. In spring mass system, the equation of spring mass system is mx double dot plus kx is equal to 0. Now, in this expression, how many dots do you have? You have 2 dots. So this is called as the second order differential equation. Now, first, we have to identify something called as the state space, which means which are the most important variables that describe the behavior of the system, state of the system. What is the state space? So the idea to do this is, it's a second order system. So there are going to be 2 states. Why 2 states? Because this is the second order system. First state will be the state with the derivative 0. So can you see that there is no derivative to x? So my first state is going to be x. My second state would be the derivative of first state. So for the second order system, my states are going to be the state with the 0 derivative. Can you see that there is no dot on here? So the derivative x is the state with 0 derivative, and its next state is x dot. So x and x dot are the 2 states. So in the line number 2, I'm going to specify these 2 states. My first state is the derivative. First state is the displacement. Second state is the velocity. X is the displacement. X dot is the velocity. Everyone understood this? If I have the differential equation of x triple dot, that simply means that I would have 3 states: x, x dot, and x double dot. Now here, the system states are x and xd, where x is the displacement, xd is the velocity, g is the gravitational acceleration. I just put it there, no need. Mass is the mass 0.1 kilogram. That is the mass attached to the spring. K is the spring coefficient and D is the damping coefficient that I wrote as 0. Now go back to the notes. For this system, we have T, which is the kinetic energy, which is 1/2 m x dot square, and I have V, which is 1/2 k x square, and my Lagrangian is T minus V. So what I did is I substituted on line number 8, I substituted the Lagrangian. Everyone understood this? And that's it. Everything else will be taken care by the script, but I will go line by line. Now your states are X and XD. Currently, there are no external forces on the system. On the spring mass system, on the right-hand side, you have 0. It means there are no forces. So that's why there are no generalized forces. There are no internal forces. And we will talk about the energy dissipation and damping. But for the time being, that since D is equal to 0, R is equal to 0. Everyone understood this? So whenever you use this script, the most important thing is identify your states. Find out the kinetic energy. Find out the potential energy and form the Lagrangian. Everyone understood this? Once that is done, what you do is you invoke this Euler-Lagrange function. You invoke this Euler-Lagrange function, and you need to give a little bit of delay so that that function runs, creates the Simulink file, creates the MATLAB script, and so on. So then next thing is here I'm performing the numerical simulation. So let me give you the syntax of the code. So on line number 16, Vs is the output, Euler-Lagrange is the function, L is the Lagrangian, X states, Qi, Qe are parameters, generalized forces, internal forces, and parameters. M indicates that we are going to create a .m file. So it will generate a MATLAB file. S indicates a Simulink function, so that this code will generate a Simulink function. And what would be the name of that MATLAB file and what would be the name of the Simulink function? The name would be ODE2. So what I'm going to do is I want everyone to pay close attention. In this workspace, I have this ODE2.m. So what I'm going to do is I'm going to delete this. I'm going to delete this ODE2 block.m. Delete this. Now, as you can see, in my workspace, I do not have a MATLAB function. I do not have a Simulink block. Everyone understood this? Now I'm going to run this code. This code will find the differential equation, form the differential equation as a MATLAB code, MATLAB script file, run the differential equation solver ODE45, and then give you the solution and also generate the Simulink block. How cool is that? So I'm going to run this, and now I want you to watch the folder. So I'll run this. Can you see ODE2.m got generated? And then it's still busy because it's creating the Simulink block. So, and yeah, OD block 2 dot always m dot open. So now what I'm going to do is, if you go here to the MATLAB code, you would get these plots. So one plot is for the displacement, other plot is for the velocity. So you can actually
Let me clear all. Oh, clear all. You see. Now, okay. Again, let me delete this. And I will run this code. Now it will run through all this. It will be busy for some time. And now I want you to notice it created ODE2block.m and it created ODE block SLX and it actually generated the plots. Now let me open this ODE block SLX. If you open this ODE block SLX, this is basically the Simulink block. What it means is if you want to use a Simulink solver, you can use a Simulink solver and solve the differential equation in Simulink. And I will show you very quickly how that works. So yeah, right now it's giving me an error because it's on the same path. But what you do is basically you have time. So you can go to library browser. You will find an integrator. You would add an integrator here. Okay, so you would see Simulink, commonly used blocks. Then what you will do is you will go to the integrator. Here is the integrator. You'll take this integration from here. Then you need to feed this back here again. Here again. And then what you need is you need a clock. So, or you can connect that to ground. And then basically you can run this code. So yes. Yeah, so you can connect it over here and then you can run, or you can actually connect this to the ground and then it will run. So let me show you how the solution looks like. So you can connect this to ground so that it will take the system time, or you can add it to a clock so that you will have your simulation time. And then you can actually run this script and then you will get the plot, which is nothing but the same plot that you got from your MATLAB function. So this plot is similar to the plot that you have over here. So, and again, if you want to change the initial conditions, you will have to go to this integration and you can change your initial conditions here. And those will be the initial conditions for X and X dot. So this is how you will use this MATLAB code. And ODE2.m is actually the MATLAB code or the function that takes that differential equation and writes that differential equation in a state space form so that the ODE45 solver can solve it. And I'm pretty sure that all of you have seen how to solve ODE functions using MATLAB, right? Did you guys do that webinar? How to solve the very first assignment? Yeah. How to use MATLAB? Yeah. So that's what it does. So basically, if you look at this code, you are creating this function ODE2, and then you are actually plotting subplots. You are getting the displacement, and you are getting the velocity. So how do you solve a robot problem? Now here is the most important thing. If you look at the robot, first you will find out the forward kinematics. After you are done with the forward kinematics, you will find out the velocities of each and every joint, which means you will actually have maybe 2 links, or maybe you will have 3 links, or maybe you'll have 4 links. So you will find out the rotational and translational velocities of each link. You will find out the rotational and translational kinetic energy of each link. You will add all that, and that gives you your total kinetic energy. Then you will look at the robot and you will see the springs. You look at the masses and you will find out the total potential energy for the entire robot. It means you will add the potential energy of the first link, potential energy of the second link, potential energy of the third link, and you will add all these potential energies. So now at the end, you will formulate a Lagrangian. So kinetic energy minus potential energy. And you will run this code. And once this code is run, it will give you the solution of that robot. Everyone understood this? Now what you can do is from here, you are gonna get the joint angles, you are gonna get the joint velocities. You can feed these to your digital twin. And then you will notice that your digital twin will show the dynamic behavior based on the mass, spring, damper, and other parameters or inertia properties of the robot. So that is how this whole system would work. So any question?
And where are we getting those output values?
If you go to MATLAB, you get this in figure. And if you go to equation, run this first, you will see that there is a subplot. So this is the differential equation solver. So T is the time, Y is the state. The first state with respect to time is the displacement versus time. The second state versus the time is the velocity versus time. So we did not calculate the eigenvalues here because this is not solving analytically. It's actually solving numerically. Our job is to find out the potential energy, kinetic energy, use MATLAB. Everyone understood this? Okay. I'm going to stop here, but I want to use a couple of minutes to.
Whatever you taught, all the math and the examples, all stand when we have acceleration of constant. First, we are solving projectile equation. Then this energy conservation as well. That means cannot go in with
Acceleration is not constant. Acceleration, even if you look at this plot, let me show you. So displacement is sinusoidal. Do you agree the displacement is changing? Velocity is sinusoidal, which means the velocity is changing. Acceleration is the derivative of velocity, so acceleration will also be changing. So in life, nothing is constant, everything changes. Okay, I want to take, I'm going to stop here, but I would like to take a couple of minutes to discuss